Hello everyone, in this video we're going to derive Cartesian equations for ellipses and hyperbolae, both at the same time, starting from their definitions as a loci of points satisfying certain conditions. And the conditions that have to be satisfied are summarized in this diagram, where we have a set of Cartesian axes. We have two fixed points at plus or minus c on the x-axis, where c is some positive number. We've got some arbitrary point, which I'm going to call p. Because it's arbitrary, we can just say its coordinates are x, y, and I've labeled two distances, d1 and d2, which are the distance from minus c0 to p and from c0 to p respectively. Now the defining condition for an ellipse is that the sum of d1 and d2 is a constant, while the defining condition for a hyperbola is that the absolute value of the difference between d1 and d2 is a constant, and therefore we can summarize both of those conditions in this equation where I've put them together by using a plus or minus sign. Now in this equation, a is just a positive constant. If you're wondering where this factor of 2 came from, well, it's purely conventional, and you can go through the exact same derivation without that factor of 2. However, you'll find that your final equation for your ellipse or your hyperbola doesn't come out quite as neatly, and you'll have to be aware that your value of a won't have the same interpretation that it conventionally does, right? So my point is there's nothing fundamental about that 2, it just makes things work out more neatly. So let's start by coming up with expressions for d1 and d2 in terms of the various parameters of the problem. And we can do that pretty easily by considering Pythagoras. And think firstly about the right angle triangle with d1 as its hypotenuse and with horizontal and vertical base and height. And then you'll conclude that d1 squared is equal to, well, the difference in x coordinate between these 2 points is just x minus c, which is x plus c. So I have to do x plus c squared. Similarly, the difference in y coordinates is just y, because this point down here has a y coordinate of 0. So I have to add on y squared. I'm going to expand the brackets and regroup the terms just to make this look a bit nicer, and we'll get x squared plus y squared plus c squared plus your cross term 2xc. And then for basically the same reason, you conclude that d2 squared is x minus c squared plus y squared, right? The only difference is now we're considering the distance between these 2 points, where the one on the right has a positive c as its x coordinate. You then expand the brackets again, you get something very similar, x squared plus y squared plus c squared. This time you've got minus 2xc at the end. Now what we want to avoid is having to take the square root of these two things and then sub them back into the original defining property, because then you're going to lead to something which you just can't make much algebraic progress with because you've got square roots all over the place. So instead, we'll go back to that defining property and just square everything so that we can use our squared d1, d2 expressions directly. If we do that, we get d1 squared plus d2 squared plus or minus 2d1 d2 is equal to 4a squared. Note that we don't need modular signs in that equation anymore, because when we squared our defining property, we made everything positive anyway. Now actually this 2d1 d2 term is not very nice, because if you imagine taking the square root of this and the square root of that and multiplying those by each other, you're going to get something that doesn't simplify very nicely. So ideally we need to square everything once again so that we can just work with squared distances. Before we do that, let's put the cross term on its own so that we don't get loads and loads of terms when we expand the left-hand side. So we're going to get plus or minus 2 d1 d2 is 4a squared minus d1 squared plus d2 squared. So let's square our equation once again. When I square the left-hand side, the plus or minus is going to disappear. That's a very important point, which I'm going to say more about later on. For now, let's just note that it's 4 d1 squared d2 squared on the left, and the right hand side I'm just going to put big square brackets around everything and do 4a squared minus d1 squared plus d2 squared all squared. So there are two important quantities in this equation. There is the product of the squared distances and the sum of the squared distances. So let's just take a moment to work out what those two things are in terms of x, y, and c. So d1 squared, d2 squared, just the product of this and this. And that's a difference of two squares if you view x squared plus y squared plus c squared as just one term, right? Because you've got that stuff plus 2xc times the same stuff minus 2xc. So if you use your difference of two squares identity, you're going to get the first thing squared, which here means x squared plus y squared plus c squared all squared, minus the second thing squared, which is going to be 2xc all squared, or 4x squared c squared. Then we've got to think about the sum as well, d1 squared plus d2 squared. Again, just look back at those two expressions on the left. The sum is pretty easy because the 2xc's just cancel out and you get double the rest of the terms. And so we can write that as 2 times x squared plus y squared plus c squared. So let's sub all of that back into our equation up at the very top there. The left-hand side is going to be 4 times all of that. And so that's going to give me 4 times your squared bracket, x squared plus y squared plus c squared all squared, and then minus 16 x squared c squared. The right-hand side, we've got 4a squared minus this all squared, right? Because d1 squared plus d2 squared was 2x squared plus y squared plus c squared. So we're going to get 3 terms when we expand our big squared square brackets in our equation at the top. 4a squared squared is going to give you 16a to the 4. Your distance term squared is going to give you 4 times x squared plus y squared plus c squared squared. Then you're going to have the cross term, which is 2 times this with a minus sign. 2 times 2 times 4 is 16, and so this is going to be minus 16a squared into x squared plus y squared plus c squared. Then some very nice simplifications happen. You've got 4x squared plus y squared plus c squared all squared on both sides, so those just disappear. The remaining terms all have a coefficient of 16, so we can just divide out that 16 and get a simplified version, which is just minus x squared c squared is equal to a to the 4 minus a squared into x squared plus y squared plus c squared. So now I want to put the x's and the y's on the same side and all of the constant terms on the other side. So let's put the x's and y's on the left. If we expand these brackets and move our other x term over to the left, you're going to have an a squared x squared on the left. So overall, you're going to have a squared minus c squared x squared, combining it with that term there. Your y term is just going to be plus a squared y squared on the left. Your constant term, when you expand these brackets again, you get a to the 4 minus a squared c squared. You can factor out an a squared from that and write it as a squared into a squared minus c squared. Now at this point I'm going to impose 2 restrictions on a and c. Firstly, I'm going to say that a shouldn't be 0. I guess earlier I said that a should be positive. Let's now make it explicitly clear that that doesn't include 0. I also want to make sure that a is not equal to c. The reason it's important to impose those restrictions is that, well, if a were 0, then the coefficient of y squared would be 0. If a were c, then this and this would both be 0. And you get various special cases of these loci if those conditions are not fulfilled. Those are called degenerate cases. It might be interesting for you to think through what shape those loci would have. You get points or line segments depending on which combinations of those conditions is satisfied. But for the rest of this video, we're going to focus on the more interesting and more general case where a is not 0 and a is not c. So what that allows us to do, because the right-hand side is definitely non-zero, is to divide everything by the term on the right-hand side. That's going to mean that your x squared term is now just x squared over a squared, because the a squared minus c squared would cancel. Similarly, your y squared term is y squared over a squared minus c squared, because the a squareds cancel, and the right hand side is just 1. Now what we have here is indeed a simplified Cartesian equation. The complication, however, is we only have one equation, right? But we started with 2 distinct conditions. In our original defining property, there was a plus condition and a minus condition. So what we want to do for the rest of the video is make sure we clearly understand how it is that these 2 distinct conditions ended up giving us only one equation. In other words, how one equation can be representing 2 different loci. Of course, mathematically what's happened is that we squared this equation down here and we made that plus or minus sign disappear. So the plus or minus didn't make it into our final equation, but we want to gain a bit more of a deep understanding of what's going on here. So the first step I want to take towards understanding what's going on here is to consider the x and y intercepts of these loci. So the x-intercept will occur where y is equal to 0. If we set y equal to 0, then we get x squared over a squared is equal to 1, and therefore x is equal to plus or minus a. So this is fine, and it's interesting because it tells us that your ellipse or your hyperbola will always intersect the x-axis at 2 distinct values, plus or minus a, right? That will always happen. What happens if we look into the y-intercept? If we set x equal to 0, well then you get y squared over a squared minus c squared is equal to 1. And then of course you get y is plus or minus the square root of a squared minus c squared. Now, because of that square root, this is not always a real number. It will depend on the relative size of a and c. So that means your locus may or may not actually intersect the y-axis. So let's consider individually the two cases where the curve does and doesn't intersect the y-axis, and then we'll see how that links to the concept of there being two different types of locus, the ellipse and the hyperbola. So let's say case 1 is going to be where a is bigger than c, therefore a squared is bigger than c squared, and therefore the square root of a squared minus c squared is a real number, which is to say that the curve does intersect the y-axis. Now, if you go back to the diagram up at the top left and you consider any point on the y-axis, let's say this point here, then by symmetry, the distance from that red point to minus c0 and plus c0, those two distances will be equal because the y-axis is the perpendicular bisector of the line joining those 2 points. So we've established that d1 and d2 are equal at any point on the y-axis. That would mean that the modulus of d1 minus d2 would be 0. And if we refer back to our defining equation there, that would suggest that if we were to take the minus sign, then a would have to be 0. But we said that a is not 0. So the conclusion of this contradiction or apparent contradiction is that if a is bigger than c, then we must have taken the plus sign in our original definition, right? So I'm going to make a note of that. This case 1, where a is bigger than c, has to be the case where we took the plus sign. Modulus of d1 plus d2 equals to a. Otherwise, we end up with a contradiction. So what we usually do then is rewrite our Cartesian equation in the form x squared over a squared plus y squared over b squared is equal to 1, where b squared is a squared minus c squared. And this is fine to do because in this case, a is bigger than c. Therefore, the right-hand side is a positive quantity, so we may as well call it something squared. And of course, this is the ellipse case because we said this corresponds to the plus sign in your defining property. So we've successfully derived our standard Cartesian equation for the ellipse, and in addition, we've derived this standard relationship that b squared is a squared minus c squared for an ellipse. What about the other case? Well, let's call it case 2, and it's just going to be the opposite of case 1. This time a is less than c. The square root of a squared minus c squared is not a real number, meaning, referring back to this, meaning that our locus in this case doesn't intersect the y-axis. Well, how does this relate back to our defining property over here? Well, we've already argued that if we take the plus case, we would expect two different y-intercepts, and therefore the minus case must correspond to the a less than c case where there are no y-intercepts, right? So we kind of have to deduce that case 2 is really the case where we would have started with the minus sign. The modulus of d1 minus d2 is 2a. And in terms of how to write your final equation, well, we keep our x squared over a squared. Now a squared minus c squared is a negative quantity. So what we do is put a minus sign in front of the y term, write it as minus y squared over b squared is equal to 1. This time b has a different definition, right? This time b squared is c squared minus a squared, and this of course corresponds to your hyperbola. So there you go, we've managed to simultaneously derive the equations for an ellipse and for a hyperbola, taking special care at the end to understand how a single equation, this one here, can lead to two different cases, even though our plus and minus sign disappeared at some point during our working. So thanks for watching, I hope it's been useful, and I'll see you soon.